Welcome back, ladies and gentlemen. We're going to be taking a look at the biogeochemical cycles, specifically the carbon cycle, which you can see here in this nice picture. It's a little small, so let's take a look at some bigger pictures. But first, a little definition. Biogeochemical cycle. Oh boy. While energy flows in a one-way direction through the ecosystem, right, from the sun to the producers, to the primary consumers, to the secondary consumers, all the way up until it gets to us, at whatever point we decide to step in, nutrients are recycled. Abiotic nutrients, so non-living nutrients, are recycled throughout the system. These recycling cycles, are called the biogeochemical cycle, and is the process by which nutrients move through organisms and the environment. The important nutrients that are recycled are carbon, oxygen, and nitrogen. Those are the key ones that we're going to be looking at. Now, oxygen, it's kind of obvious. You breathe, you know how that works. We're not really going to touch that one too much. We're really going to take a look at carbon and oxygen. Now, biogeochemical, let's break it down. It's a big word, but break it down. Bio, living thing. Geo, geography, earth. Geo means earth. So the living earth chemical cycles. I've said it before, I'll say it again. Scientists are bad at naming things. So what are we looking at here? We're looking at the living earth chemical repeating patterns. That's it. That's all this is. It's just a big word to say that. Now, admittedly, there's no real short way to say that, so I'm not surprised to have a big word for it, but that's all it means. Living earth chemicals moving in a cycle through all living things. Okay? All right, let's take a look. Carbon is a key element for all living things. Carbon can be found everywhere. You are a carbon-based life form, as is your pets and your siblings, assuming that they are also still alive and you haven't been really angry at them over the course of this shutdown. But either way, all of these organisms are based in carbon. Now, there's a reason for that. We talked about this in chemistry class, right? When we were talking about the fact that carbon is incredibly flexible. And that flexibility allows carbon to bond with so many different things. It can be covalent. It can be ionic. Well, mostly covalent. It can be covalent. We'll go with that. And as a result of that, it can do a ton of stuff, including being alive. Carbon can be found in the atmosphere, dissolved in the oceans as part of inorganic carbon dioxide, right? The carbon in the air is recycled into more complex organic substances through the process of photosynthesis. Now, okay, you know how photosynthesis works. You've done this before, but just a little bit of a reminder here. Photosynthesis is the process in which a plant makes their own food from water, carbon dioxide, and light from the sun. It uses this to produce energy, and that energy is stored in the form of sugars or oils or starches. So here we got a very complicated looking diagram. Take a look at the details, right? You got light coming in, you got water coming in. It's going into these parts of the cell here with these very fancy technical names, but as a result, oxygen comes out. That's important. That's what we need. This process produces the energy that the cell needs. That energy is then also uses some carbon dioxide in order to make some sugar. And there you go. Yeah, all right, there's a bunch of steps and details in there, and if you decide you want to become a botanist and learn all the details about this, go right ahead. But that's the basics, right? This is the basics of how these things are kind of coming together, and you know these basics. You've done them before. You've seen them before. For this process to take place, the chlorophyll must be present, which is found in green plants. The general equation for photosynthesis is this. Hey, it's chemistry equation. Oh, you thought you escaped them. I'm afraid not. Chemical equation. Look at this. All right, wait, break it down. I know it's been a while. Break it down. Carbon dioxide, CO2, plus H2O, good old dihydrogen monoxide, water, it's water, combines to produce this, which is a carbohydrate. That's the fancy way to say sugar. This and, of course, oxygen. Originally, way back in the mists of time, there weren't animals that consumed oxygen. There were only plants. Oxygen was a waste product, right? Like plant poop. It's not exactly the same, but it's a waste product. And as a result of that, it started to build up in the atmosphere, and it was a problem. So other animals, other organisms, I should say, evolved into animals consuming the oxygen, allowing a balance to be maintained in the ecosystem. See, there's a balance thing coming up again. Balance is complicated. It takes time. All life on Earth, with the exception of very few bacteria, depend upon the process of photosynthesis. There are some bacteria that can live without photosynthesis, and there are some organisms beyond just bacteria in deep sea oceans and things like that that can also live. There's a bunch of videos that I've posted in the plan. I really recommend looking at them. A lot of them are pretty cool. There's stuff like the underwater lake and blood falls. I know it sounds weird. Take a look at them. Cellular respiration. Let's keep going. The process in which all living things release the energy that is stored in their food, aka those sugars. So it takes place in a cell in an organelle called the mitochondria. Although here it's mitochondria, and that's the singular version as opposed to the plural. That doesn't matter. Point is, sugar comes in, some kind of chemistry happens, carbon dioxide comes out, as does some water, aka pee, and carbon dioxide that you breathe out, and that produces this ATP. That's what you need to like move around and think and do stuff, right? Sugar gets turned into this ATP chemical in order to live. So there you go. What does that mean? Well, what's so crazy about this? Well, here's the crazy part. There is the general equation for cellular respiration, and what do you notice about it? It's basically exactly the same as photosynthesis. It's just backwards. Photosynthesis takes water and carbon dioxide plus energy to make oxygen and sugar. Cellular respiration takes sugar and oxygen to produce carbon dioxide and water and, of course, energy. So this whole process basically consists of take the energy from the sun, store it for a little while, then use it later. That makes sense, right? Like you're not eating 24/7. It might seem like you do. It might seem like you're very hungry and you're eating all the time. But you do not physically have to eat at all times in order to not die. You have the ability to store energy for use later. All organisms are like that because, well, almost all. Because any organism that isn't like that is incredibly fragile and it will die if there's any disruption. Could you imagine, right? The sun goes down, photosynthesis stops, all the plants immediately die because they have no more energy, no more food. Well, no, they don't. They sleep during the night and they wake up during the day and keep going. How? Because they stored the energy from the day in the form of sugars, starches, and oils. Similar, you eat 3, 4, 5, 6 meals a day plus snacking, but you're not eating every second of every day because you can store the energy that you have consumed in the form of, in the case of animals, fat. Fat gets a bad rap, but all it is it's a battery. That's your battery, right? Like, you need a battery for your phone for it to work. If you've got too big of a battery, your phone's too heavy. That's a problem. That's it. It's all how it works. Photosynthesis and cellular respiration are part of the cycling of matter, the transfer of energy in an ecosystem. They are a key process in the carbon cycle. Okay, carbon cycle is a process by which carbon moves through the ecosystem. Let's do some examples here, okay? This is something on your book here. You can fill it in. We're going to start up here at the top here. We're going to start with combustion. Okay, so we're burning wood and fossil fuels, and that is going to put it, boom, CO2 in the atmosphere. Okay, we'll talk more about that in just a little bit, but here's the rough idea. So here's the cycle in its entirety. Now we're going to take a look at number 3, right over here, and we're going to see photosynthesis takes the carbon dioxide from the atmosphere and it turns it into sugars. Now, we're going to go for number 4. We're going to go here. There's a lot of different branches, but we're going to go for 4 right away. Primary consumers then eat the plants. Duh. Those get, of course, eaten by higher level consumers, secondary, tertiary, whatever, quaternary. This, of course, then turns into cellular respiration, which puts the carbon back in the atmosphere, right? The plant here turns the carbon dioxide into sugar. This guy eats the sugar, he eats this guy, and then he breathes out to produce carbon dioxide again. So this is a very tight and closed circle right here. But there are other circles. So where do those come from? Where do those go? Well, instead, the tree could die before anything eats it. I know, crazy talk. If that happens, it becomes detritus. Remember that word? It's a big, complicated word, just basically means garbage. Detritivores, the ones that eat garbage, will then break down this particular matter in a process that's basically cellular respiration, meaning that you will get decomposition, which turns into a form of cellular respiration because those organisms are alive, and that releases it back into the atmosphere. So this whole system recycles the same carbon dioxide throughout the entire atmosphere. Right now, Your body could be made from carbon that was once a dinosaur. Yes, one of the cool dinosaurs. Obviously. You wouldn't be one of the not cool dinosaurs. Okay. All of that tied carbon to the atmosphere and to living things. But there is that little hint off to the side of the combustion. There are actually 4 places to store carbon, 4 reservoirs, for lack of a better word. The first one that we've seen is the atmosphere, or the air. The atmosphere plays a central role in the carbon cycle because here you can find carbon as carbon dioxide. Atmospheric carbon dioxide enters the terrestrial, it means land, terrestrial means land, terra means land in a Latin, food chain through plants when they perform photosynthesis. So we just talked about that. So this is like summary of the last couple slides. Okay, so the atmosphere stores carbon dioxide. That carbon dioxide gets into living things through photosynthesis. Okay, what's the next one? The ocean, water. Ocean plays a major role in determining the carbon dioxide levels of the atmosphere. I wonder why. Carbon dioxide can dissolve in ocean water and returns to the atmosphere when it spontaneously comes out of solution. Basically, if you leave a glass of water out, carbon dioxide can sort of dissolve into it and it will build up and build up, much like, you know, there's a bunch of markers in here, right? So if there's tons and tons of markers in here, there's lots of carbon dioxide. I could put more things in here, putting more carbon dioxide. But it's also possible for some of it to come out, go back in the atmosphere. There's a balance to this, just like everything else we've talked about. No shocker there. The carbon is returned to the water when aquatic organisms respire. Oh, I missed this line here. Carbon leaves the water when it enters the aquatic food chain via photosynthesis. So it's the same thing that happened on the terrestrial, the land-based food chain, but you know, now it's in the water, so it's wet. Then the carbon is returned to the water when the aquatic organisms respire, aka do cellular respiration, and release the carbon back, just like we talked about in the previous slide with creatures on land. So the water and the land basically do the same thing here. So we've talked about living things a lot. Let's take a look at those living things. Living organisms. Kind of think of them as fire, maybe. We had air, we had water. Kind of got fire. Living things are kind of alive like that, right? Some of the carbon picked up by the plants returns to the atmosphere as carbon dioxide when plants respire. The rest of the carbon is used to build plant tissues like starches, oils, cellulose, sugars. The carbon then either moves through the food chain, beginning with herbivores when they eat the plant, or to decomposers when the plant dies. Animals and decomposers return the carbon to the atmosphere as carbon dioxide when they respire. So we've got it up in the atmosphere. It can go into the ocean or into living things on land. If it gets in the ocean, it could go back in the atmosphere, or it could go from the ocean into more living things that are underwater. And then they can go back up to the atmosphere. So it's just a cycle. It's just going like this. But there's one more piece of this cycle that's very important, absolutely critical. The Earth. And hence why I had that whole 4 elements thing going. Eventually, carbon from other reservoirs becomes trapped within stones and especially fossil fuels. This is a long-term storage that can take millions of years to unlock through either erosion or volcanic activity. So an example here. You've got peat, right? That's a type of like material made from dead plant matter that dies and it lands on the ground and it starts to decay and fall apart. The carbon that made up that plant matter doesn't disappear. It just falls and breaks into simpler and simpler things. Over a long time and a lot of pressure from, say, stone or water pushing down on it, that dead organic matter hardens and turns into stone, coal, oil, natural gas. All of these came from living organisms that have since died. So the Earth acts as a long-term storage for all of the carbon dioxide. It's like the hard drive on your computer where you put all your pictures. You stick them back there, you never look at them again. The living sphere, the biota, the ocean, and the atmosphere cycle things much faster. They go like this, crazy. But the Earth, long-term storage. Okay, we got the Earth, we've got the water, we've got the air, and we've got the fire, the living things. That's a lot to keep track of. Let's put it together. Let's get ourselves a picture. Here we go. We got ourselves a nice picture. What do we see? The Earth, the geological, is storing it long term. through erosion and volcanoes, I might be able to release that back into either the ocean or, more likely, volcanically, the atmosphere. The atmosphere is another major place to store things, and that atmosphere releases carbon into living things, the biota, and into the ocean directly, which can then be linked into the living things as well. All of these systems cycle together, working in this constantly regenerating loop over and over again. But sometimes things happen that disrupt it. For example, a forest fire. A forest fire will burn trees. As you burn trees, you will release a large amount of carbon dioxide into the atmosphere. You can also see this, instead of a forest fire, maybe a farmer might burn the grass and stubble left over on his field, or burn leaves. This will release the carbon trapped in the living things into the atmosphere. A volcano, I already mentioned that one. A volcano will break down the rocks and release the carbon that was stored in the long-term storage. But that's not the only thing. It's got another way that it affects things. The ash generated by the volcano, the pieces of rock and burnt material that get thrown up in the air, they stay up there for years and years, decades. And when they do that, they reduce the amount of sunlight that reaches the earth. The sunlight is reduced. That means that the plants don't have enough energy to make sugars. They don't pull as much carbon out of the air. So we put more in there and we're taking less out. Overall, that increases the amount of carbon dioxide. That's subtle. This point here is a subtle one. This one's obvious. Like, oh, big volcanoes releasing carbon dioxide. That seems pretty obvious. But this one, that's not so obvious. Humans can also do it. I know. You were waiting for it. You were like, oh, what are humans doing? Deforestation. We chop down trees all the time. That's what all this paper is made from, right? If you chop down trees, guess what? There are now less plants to pull carbon dioxide out of the air. What does that mean? You're going to have more carbon dioxide sticking around up in the top atmosphere. Not just that, if you cut down those trees and then you burn them, which we do, we burn wood for fuel and stuff, well, then you're going to release the carbon that's already trapped in the trees into the atmosphere. And a big one for us, combustion of fossil fuels. This is a huge one. The modern world is built on fossil fuels in a lot of different ways. But there's a problem. Stone, the earth, the geological here, that is a major place for us to store fossil fuel, for the earth to store carbon dioxide. But we dig that stuff out of the ground and we burn it every day, all the time. Normally, it stays down there for millions of years. Not anymore. We drag it out of the ground and we light it on fire. What does that mean? It means that overall we're pumping carbon dioxide into the atmosphere. Carbon dioxide that would have originally been trapped underground gets shoved up in the atmosphere by combustion and then goes into the oceans and into the biosphere as a result. This has huge effects, global warming being one of them. As we've kind of seen, global warming, of course, is also generally called climate change because, yeah, the overall Earth gets warmer, but that doesn't mean that your area of the Earth doesn't get colder. This has been the single biggest effect that we've noticed in terms of the biogeochemical cycle. And, of course, the modern age. Now, there are some examples that we can look through for this. I recommend the video Door to Hell. Looks like that. Doesn't that look exciting? I wonder what it's about. You'll find out when you take a look. The video is in the link, of course. You'll also see that there's going to be a bunch of practice that you can work through in your book once again. But we're not completely done yet. I'm not going to see you off just yet because I have one more thing I want to show you, but I have to pull it up. Little movie magic. Here we've got a comic that was done by XKCD. It is an excellent one to talk about the nature of how carbon dioxide is changing things. So what we've got here is basically a geological record. So this is a geological record over literal billions of years, trying to track as best we can how the climate has changed. Now, you might go, whoa, how do we do that? Well, we can get core samples by digging very deep in the earth, and we can try to collect information based on what we can find through some archaeology of sorts and geology. So it's possible, but we're not talking like we're going to get specific temperatures for each day of the year or something. No. We're talking that we can get an overall picture in broad strokes. Okay, so this is very broad, very, very broad. But that's okay, because we're going to be doing things pretty crazy. Now, what it says here is that the center line here is 0 degrees compared to like the 1960s to the 1990s. So this is what we kind of normally expect. So back here we see at the start, we're at 20,000 BC, and we're 4 degrees colder than it is during the 20th century. Okay? And if we keep going here, we see that, like, Boston is buried under a mile of ice, glaciers are at New York, but the world is about to warm up. Okay? This is the end of the Ice Age. By this time, humans have already spread across Africa, Eurasia, and Australia. They've created paintings, pottery, rope, bows, and arrows, but they haven't developed writing or farming yet. Remember farming? Farming is our most important development. And you'll see here that we're way over here at about -4. Changing the Earth's orbit means that more sunlight reaches the polar ice. As a result, that polar ice starts to melt. Temperatures have been creeping upward, but around this point, CO2 levels start to climb. And then the warming starts to speed up. It doesn't look like it's sped up much, like it's still the lines over here, but you can see, look, it's starting to go this way, it's starting to go this way. It's still pretty cold, though. There's a lot of limits on this data. Short warming or cooling spikes might be smoothed out by the reconstruction, but only if they're small or brief. So it sort of shows here, right? There's a lot of little zigzags that could be happening. The line hasn't moved much. In what is now France, humans paint murals on the walls of the Lascaux caves. And now things start to pick up speed. Ice sheets around Alaska shrink, exposing a land bridge between Asia and North America. Humans reach North America. 14,000 BC. The edge of the ice withdraws from New York City and retreats north. Ice is moving to Canada. The ice knows where it's at. Humans figure out that dogs are cool. Okay, you can live with us, but we'll still get mad if you poop on the floor. Deal. And we get to make you tiny and dress you in little costumes. Whoa, I didn't sign up for that. The woolly rhino goes extinct because we hate it all. Washington State is scoured by huge floods as glacier dams burst and lakes of meltwater flow into the sea. Ice sheets withdraw from Chicago. Humans settle in Syria. Temperature starts to decline. This may be caused by changes in ocean circulation or as floods of cold water flow into the Atlantic and as the North American sheets melt. It's hard to really say. This cooler period is called the Younger Dryas. Humans reach Argentina, so we're all over the globe at this point. Warming continues. Humans settle in Jericho. You may have heard of that place. First development of farming. We finally got it, and look at that. We've been doing farming now for about 9,000 years, give or take. Pretty decent experiment. Okay, and now look, boom, saber-toothed tiger goes extinct, and we're almost at average levels. There we go. The last North American Pokemon goes extinct. Okay, he's making fun here. This is a comic, right? He does science stuff, but he also has some fun things. Temperatures reach modern levels, which means that the land bridge between North America and Asia is severed, separating the two continents forever. Well, until 14-something. We figured out cows are cool. Ice sheets are gone across to Canada. The temperature starts to level out. Warm, stable period is called the Holocene climate optimum. Jiaihou is settled in China. Final collapse of North American ice sheets leading to a rapid rise in sea level and a period of cooling in the northern hemisphere. As sea rises to their modern levels, Britain is cut off from mainland Europe. At this point, England, the UK, was still connected, but not anymore. Now it's an island. Humans develop copper. Massive volcanic eruption in Oregon create various crater lakes. We just got copper mining, copper metalwork. Gold metalwork. We invent the wheel. Hey, look at that. We got the wheel. It only took us an extra 4,000 years after we figured out what farming was. The Earth begins to cool just a little bit. We start to develop the Proto-Indo-European language, basically meaning that we have the ability to start coming up with all the languages that will turn into both Indian languages and European languages. Permanent settlement in the Fertile Crescent, aka the Middle East. We figure out that horses are awesome. Minoan culture arises on Crete, 4,000 years BC. Egyptians figure out mummies are cool. We get a civilization in the Indus Valley. We invention writing in Sumeria. This is still really ancient history, but you'll notice temperatures have stayed pretty much the same. Earliest human whose name we know. The 3 sovereigns and 5 emperors of China, the Gilgamesh, Imhotep, the Great Pyramids are built. Stonehenge is complete. This is ancient, ancient stuff. Chariots, alphabetic writing. The last mammoths on tiny Siberian islands go extinct. Iron smelting. Olmec civilization in Central America. The setting of the Iliad and the Odyssey. The invasions of the sea people, we think. The Polynesians explore the Pacific Oceans. The Neo-Assyrian Empire, the rise of Greek city-states, the first Olympic Games, 1000 BC. Buddha, the stuff in the movie 300, but like at regular speed with more clothing. Mayan hieroglyphs, paper is invented. Roman Empire, Jesus, the 3 Kingdoms period, the Gupta Empire of India. Muhammad, Attila the Hun. The Tang dynasty. These are all still very old from the modern day. The medieval warm period in Europe and some northern regions, too regional to be affected, but now, there's a little bit of a dip. The Little Ice Age, it was called. The European Renaissance. Columbus discovers North America. Newton figures out the laws of dynamics. We're now in the 1600s. Steam engines. The United States comes into existence. Telegraphs are invented. The Industrial Revolution. And look at what's happening in the last bit. The solid line is data we have measured directly. The dotted line is data that we had to infer. For most of human history, this line stayed very close to the middle. But now this line is shooting up, and it's shooting up fast. This is a span of 1900s to, in this case, 2016 when he made this. Take another look at the rest of that timeline. You can watch the dotted line as it slowly shifts over millions, thousands of years. Not millions, thousands. And for most of human history, it stayed in basically the same place until it suddenly shot up. We don't know what's going to happen. Best case scenario, assuming immediate and massive action to limit fossil fuels being pumped in the air, we might be able to restrict this to being just here. Optimistically, we might be able to figure out, get our act together, and fix it up eventually. Our current path, we're going to go here. We're going to make this planet way warmer. Way warmer. So there you go. A march through history. And what do we see? We've made a big impact in a very short time. Wow. Okay. Bit more movie magic. Take a look at the door to hell. Try some of the practice questions, see what you can do, and next time we'll talk about the nitrogen cycle, the last of the biogeochemical cycles, and probably the most confusing, if only because there's so many words that are so weird. But I'll see you guys next time.